about mass springs, right? Release the mass spring. Okay, so those type of equations, I think they give you in physics with just a cosine sign. Omega is usually the amplitude, the frequency parameter that's inside. Sound familiar? You have a parameter inside. So typically, in mass spring problems, you have something like position of the mass is something like cosine omega t, something like that. Sound familiar? All right, we have a little physics in here too. I feel it. I feel the love coming from all of you. So the Van der Pol oscillations are actually pretty interesting. I think I gave you one in class where you can have a delay equation that generates an oscillation just because if there's a delay and you want something to happen instantaneously, then it's going to overshoot and then undershoot and then it's going to go back and forth. So oscillations happen often in engineering and physics, and typically I think you learn those things in the first physics course. Physics, do you guys have a university physics type class that's required? I mean, that's the whole semester. Just went out.
I'm in it right now.
Okay, so here's the Van der Pol oscillator. It looks like this. The form before you transform it into a system of 2-second order equations, which you have on your in-class assignment, looks like this. And we call, you're always looking at position in these type of equations. And then you can now draw on your calc the first derivative of position is speed, velocity, and the second derivative is acceleration. So you expect to see some kind of equation like this with the second derivative representing acceleration, the first derivative representing the velocity, and then the state variable, which is the position, is right here. So his name is actually cool. Balthasar Van der Pol. And he did this when he was working at Philips. Rarely these days do you actually see industry-generated research coming out and interacting with academia in this way. But back in this time where he's developing these equations, industry and academia work quite often together. These days, the equations and stuff that you have are proprietary. And oscillations, if you wear a watch with any type of movement device, what comes out of the device is a 3-axial accelerometry. So you get acceleration in 3 different directions. So you're using these type of equations there. When you're walking or running, it's periodic motion. And we use these type of equations again to kind of Fourier transforms. You guys did Laplace in here, but not Fourier, right? Right. So what's important about this equation? Remember, I told you I should have probably given you a math spring or something like that, but I just wanted to bypass that and go to something that's actually interesting. This equation has something called a limit cycle. And you're going to find, has like a shape. It's unique. I'll show you some videos. They're also mesmerizing, kind of like the Lorentz attractor, when you see something, a particle moving to it. But what's interesting about this limit cycle is similar to the Lorentz attractor, that you have these 2 equilibria that's unstable. And if you start inside, it pushes it outside to one side of the attractor and then switches over to the other side. That's really complicated, actually. This is less complicated because what happens is you have just one equilibrium. You're going to find it. And if you start anywhere inside for a certain range of parameters, it's going to head towards this closed curve. So this is when you plot x prime versus x, the phase portrait. That's what you're going to get. If you start outside that limit cycle, and I'll explain what this means, outside here, it's going to start and converge outside as well. So it's the whole limit cycle that captures these trajectories and pulls it to it. So that's really important to understand because it shows you, I have a hard time teaching 103 because we just erase 90% of math in there. And they talk about DDS, discrete dynamical systems, that only have very simple behavior. The cadets in there categorize the equilibria. They talk about linear things first. They spend the bulk of the semester talking about linear things. They don't ever use complex eigenvalues, so forget about periodic. It's not there. That like hurts me. We're talking about matrices and we have no complex eigenvalues. You just like erase anything interesting and linear maps. But when you have something like this, like a closed curve like this on the plane, it means it's periodic. So this is a periodic solution. Think of the unit circle. The unit circle, if you actually took the x and y coordinate and looked at it as parametric plots, it would be a unit circle. I mean, it would be periodic. We plotted them separately. So the separate trajectories are going to be periodic. So what is happening here is that the whole periodic solution is pulling everything to it, not just equilibria. So that's why 103 is just really, really oversimplified, because they only talk about equilibria. And to date, in this class, I don't know, we're going to kick you out of the nest today. You only really talk first about equilibria, and then even what you're doing right now, you're first starting with equilibria because you have to linearize around something. But then what you're going to find is this thing is going to be unstable, so it's going to pull away. Where are the trajectories going then? They can't cross a solution because that would lose uniqueness of solutions. So it's the solution that actually attracts everything to it. What's interesting about differential equations is you only can have two things happening for most nice differential equations. You either have the attractions going to come from an equilibrium point, or it's going to come from a periodic orbit. Nothing else. Nothing else can happen for up to 2 dimensions. To get something really weird, you have to go to 3, which is Lorentz strange attractor. That's 3 dimensions. In MA 103, weird things can happen in 1 dimension. They talk about it a little bit at the end of the semester, but they skate over the fact that it's complicated. Who took the 103 in here? It's a really good class, actually. I think you learn more in there than you do in the Jedi Math class, and I'm being recorded. But, the Jedi Math class is just way too fast. But that class, you actually, if you know your basic math, then you can actually learn something in there. So in 1 dimension, at the end of the semester, do you remember them talking about the logistic model? And they talked about web plots, like they talked about cobwebbing and then converging to the equilibria. Well, it turns out if you start pulling that parameter up, you get chaos in 1 dimension with that equation. I used to get to teach the 103 advanced sections, and then I get it. Let's go for it. Let's go and talk about chaos. But you can't get chaos in 1 dimension and for differential equations in even 2 dimensions. This is the most you can get. You get chaos in 3 dimensions with the Lorentz model. Okay, any questions on this? So that's what you should see from here, that it's not the equilibria. It's going to be something, a limit cycle, but that's as bad as it gets. So let me share with you videos about that.